Mini lecture for Prepare for Class 1.2 on absolute value inequalities. This is like problem 3 in the Prepare for Classwork. I've added that we're going to write the answer in interval notation so I can be sure to talk about that. They give us an absolute value inequality. The first thing to do when solving these is make sure the absolute value is isolated on one side of the inequality. And here we can see that it is isolated. It's by itself. There's nothing added, subtracted, multiplied, or divided outside of the absolute value inequality. Because the absolute value is greater than this number, I know it's divergent, meaning I'm going to have two answer sets. But if you don't know that, even if you don't know that, you can take it at this point and make two inequality problems. I'm going to have x minus 7 is greater than or equal to 4, or x minus 7 is less than or equal to negative 4. So these are the two intervals over which this absolute value is true. And then I solve these inequalities. I'm going to add 7 to each side. X is greater than or equal to 11, or x is less than or equal to 3. So those are my solutions. If I were to graph these on a number line, I would have 3 and 11 are my significant. Even though 11's written over here, notice that 11 is larger than 3. Absolute value x is greater than or equal to 11. So there's going to be a solid dot at 11. Greater than or equal to means it's going to be moving up towards positive infinity. Or it's going to be less than or equal to 3. So again, or equal to means there's a solid dot here at 3, and it's going to go down towards negative infinity because x is less than 3. So x is anything in those solid lines. Instead of a solid dot, I could have also represented this as a square bracket, because a square bracket means that it's included, and the bracket faces the direction the solid line goes, the heavy line goes, because those are the points are all included up until 3. So this helps me. The graph helps me write the interval notation. This interval goes down to negative infinity and up to 3, up to and including 3. We can never get all the way to negative infinity, so it's always curved. When we get to the infinities, it's always curved. Now this is the union of, because it's also, all these answers are also possible answers up here above 11, greater than or equal to 11. Because 11 is included, it's got a square bracket, it goes on up to positive infinity with a curved bracket. So this is the solution to this first problem up here in interval notation. The next problem is very similar, only it's got a fraction in it. It's got a fraction in it. Don't let the fractions freak you out. We can handle fractions. Plus 4 divided by 5. I'm just going to add another number to this over here. I'm going to put a, 3 outside, okay? Because some of the problems have that number there. This one we're just asked to solve and write in interval notation. So the first thing I need to do is isolate my absolute value. So to isolate the absolute value, I note here it's being multiplied by 3, so I divide both sides by 3. This will give me 3x plus 4 over 5 is the absolute value of 3x plus 4, all divided by 5, is greater than or equal to 1/3. At this point, I'm going to split it into two inequalities, taking away the absolute value equation. I'm going to have the positive, which is just like this, and I'm going to have its opposite. So its opposite is 3x plus 4 over 5 is less than or equal to. Note I've changed the direction of the sign, and it's negative 1/3. So that's one solution. Or it's going to be 3x plus 4 over 5 is greater than or equal to positive 1/3. That will be my other solutions, set of solutions. To get rid of this fraction, I've got to multiply by 5. If I multiply one side of the inequality by 5, I multiply the other side of the inequality by 5. If I were multiplying by a negative, I would have to change the direction of the inequality. Whenever I multiply or divide by a negative, I change the direction of the inequality. This gives me 3x plus 4 is less than or equal to negative 5/3. It's all right to have fractions. I need to isolate my x, so I'm going to subtract 4 from both sides. Subtracting 4, 4 over 1, I have to change it into something over 3. So I've got to multiply it by 3 over 3, which is going to give me 12 over 3. So this side is really negative 5 minus 12 over 3, or negative 17 over 3. So I have 3x is less than or equal to negative 17 over 3. I'm going to multiply both sides by 1/3, or divide by 3. Dividing by 3 is the same thing as multiplying by 1/3. Sorry, this should have been a 1 there. Here I'm going to end up with x on one side and run out of paper. I get x is less than or equal to negative 17 over 9. So that's the lower range of what I have. And then I'm going to solve this side. Over here, the first thing I need to do, again, is I multiply both sides by 5. That will give me 3x plus 4 is greater than or equal to 5/3. I'm going to subtract 4. I already changed it to an equivalent fraction over here, so I'm going to subtract 12/3 from this side. I'm going to get 3x is greater than or equal to negative 7/3. I need x by itself, so I'm going to divide by 3, which is multiplying by 1/3. I'm going to x is greater than or equal to negative 7/9. So now I have these two ranges, intervals, that make our original statement true. So to write this as interval notation, I have to know which one's smaller. Negative 17/9 is smaller than negative 9/9. It's further to the left. So it's going to be like this if I graphed it. And this would be this way, negative 7/9. So my interval will be from negative infinity to negative 17/9 included, and negative 7/9 to positive infinity. And again, positive infinities are never included, negative infinities are never included, they're always curved. I hope this helps.